video is for Math 1342, and we're going to be learning Chapter 9, which luckily is very similar to Chapter 8. Chapter 8 is all these hypothesis tests where we check for proportions or means or standard deviations, but all of the problems there involve just one sample at a time. The really only difference in Chapter 9 is you do two samples at once. We want to compare two populations, so maybe it's men versus women, or adults versus children, or Democrats versus Republicans. So the emphasis is a little different. Instead of saying that somebody's claiming that the average or the proportion is such and such, now the claim is always about how do these two populations compare to each other. Is one better than the other? Is one worse than the other? Are they different? Are they the same? So the emphasis on some claimed value isn't really there. There'll be some numbers involved, but it's more about how does one population compare to the other. And we're going to basically do three types. There's really four types, but the three things we're going to do is the same as Chapter 8. Proportions, means, and standard deviations. And means have two different kinds of problems here. So that's why there's actually four different types. So Chapter 9, we do sections 9.1, 9.2, 9.3, and 9.4. Section 9.1 is when you're doing two proportions. So a perfect example is any kind of election, Democrats versus Republicans. Are the voters going to favor one candidate over the other? Are they equal? Are they different? Is one higher? Is one lower? Anything like that could be a claim. So two proportions are going on at once. There's three problems from section 9.1. First one says, since an instant replay system for tennis was introduced at a major tournament, men challenged 1,424 referee calls, with the result that 420 of the calls were overturned. So these are proportions. These are basically yes/no questions. They asked 1,424 referees, can I overturn this call? And 420 times they said yes. And then that's how Chapter 8 went, except now we also have women to compare that to. Women challenged 753 calls, and 229 of the calls were overturned. So there's both sample sizes and number of yeses for both men and women. The claim here says, test the claim that men and women have equal success. See, that's what you would hope, is that gender does not play a role. So the tennis association might be saying, we treat the genders equally, and the calls get overturned equally for men and women. Now, somebody might not believe that and maybe thinks that one gender has a higher success rate than the other. And if it's a significant difference, then there could be a cases for a lawsuit or some kind of challenge, and however the system is going. Okay, so since the claim is that men and women have equal success, then the way you write that is the null hypothesis for step 1 is that the proportion of men equals the proportion of women. And they usually write 1 and 2 for each one of them, but you could put M and F if you want to put proportion of males equals proportion of females. But usually they just do 1s and 2s. Since that's the claim, then the alternative needs to be exactly the opposite, which would definitely be not equal to. And us trying to prove this wrong, basically, we don't really care. Is it the men that are getting the benefit? Is it the women getting the benefit? We just want to show that somehow gender plays a role in how referees are calling things. So if it turns out men or women are higher, that's not really our issue right now. We just care about, are they equal or not? So remember, the null has to be only an equal to, so you would never put a not equal to, or, so that one's definitely out. Now, in the past, they used to put greater than or equal to, or less than or equal to, like C and D have. But I'm pretty sure they don't do that anymore. So you would only pick the one that has equal to in the null, and then that would make this not equal to. So there's step 1, doing the hypotheses. Okay, then these are easily done in a graphing calculator. If you don't have a TI 83 or 84, then you can do it by hand as well, but it's so much better this way. So stat tests, and we're going to use these 3 that have a 2 in front of them: 2 sample z-test, 2 sample t-test, and 2 prop z-test. This is the 2 prop z-test because it's about proportions. We did the 1 prop z-test back in chapter 8. Now we're doing the 2 prop z-test in chapter 9. It's very much like the 1 prop z-test. Back then, all you filled in was x, n, and the whatever the claim was. But now there's 2 sets of x's and 2 sets of n's. That's really the only thing different. So again, the x is the number of yeses. It's always the smaller number of the 2 if you're comparing men and then doing the same for women. So this 420 would be the x1, and the 1424 is the n1. X can never be bigger than n no matter what, so definitely that would be the case here. You can't get more yeses than people you ask the question to. For the women, there were 753 calls, that's N2, and then 29 yes were overturned, so 229 is the X2. And then 753 is the N2. And then we had the not equal to option, so P1 is not equal to P2. Notice the only 3 things you ever put in the alternative are not equal to, less than, or greater than. This is the not equal to. Calculate, and this will get you your z-test statistic, which is mostly used if you're doing this the old-fashioned way with critical values. And then the second number down is the p-value, and that's how we base our conclusions off. They even tell me p-hat1 and p-hat2, this is the proportion of men and women in the samples that got their calls overturned. So 29% of men successfully challenged and 30% of women. So the women were slightly higher in the sample, but it's probably not a significant difference, 29 versus 30% of the time. If I did another sample next tournament, maybe the men would be slightly higher. So when the null says they're equal to each other, it's not that they have to be absolutely equal. Just in order to say that's false, one of them has to be significantly different than the other. And probably 29 and 30% is not significantly different. In fact, it's only significantly different if you get a very low p-value, and I have a pretty high one actually. So the z-score is negative 0.445, or I don't know how many decimals they want, 2 decimals, so negative 0.45. Then they should ask for the p-value next. The p-value was pretty high, 0.656. 656, 3 decimals on that one. Okay, so the p-value is greater than, because the highest alpha they ever give us is 10%, and we're up at 65% for the p-value. So remember, if the p-value is low, the null must go, but this p-value is greater than 0.01. And actually what I would do if I was working this out is you should put the p-value down 0.656, then put alpha down, because they'll always give you alpha, but it's always between 1 and 10%. Since they're doing the p-value to 3 decimals, you should do alpha to 3 as well and add an extra 0 there. But 656 is greater than 0.10. So do not or fail, do not or fail. Those two mean the same thing, but different books word it differently. Do not reject the null. Fail to reject the null. The null says the genders are equal, and we don't have enough evidence to say that's not true. The women were slightly higher, but not significantly higher is what that's saying. So do not reject the null, fail to reject the null, fail to reject. And if there is, see, I like the other wording better. I like to say do not reject the null rather than the word fail, which means the same thing. But in some books we say do not reject the null, and then it makes the next part easy because then you say not enough evidence. Not goes with not. If you say yes, reject the null, then there is enough evidence. But if you say do not reject the null, then there's not sufficient evidence to warrant rejection of the claim. Okay, another, and I mentioned this too once we started chapter 8 in the last video, confidence intervals are kind of an alternate way to do this. So I could do a confidence interval for these two genders and see if one of these, if both answers are like significantly positive or significantly negative, then we would know that one gender has the advantage over the other. But if one answer is negative and the other one's positive, that means we're surrounding 0, and that if there's no difference between the genders, then the subtraction should be 0. So the calculator can do confidence intervals for 2 samples. It's a little strange how they teach. Let me go here, stat tests. The books all teach confidence intervals first in usually a chapter 7, and we did we didn't do Z interval, actually. We did T interval and 1 prop Z interval. Those, the number 7 and the letter A, they were taught in chapter 7. They don't teach any of the 2 sample intervals in chapter 7, strangely. And then they teach all the 1 sample tests in chapter 8 of most stat textbooks. So Z-test, T-test, and 1 prop Z-test. And actually the Z-test is a lot like the Z interval, and the 1 prop Z-test is a whole lot like the 1 prop Z interval. Then most textbooks teach both the 2 sample tests and the 2 sample intervals in chapter 9. So that's all that's going on here. If I go to, remember the 1 prop Z interval, I can do a 2 prop Z interval. We never did that in chapter 7, but now we can do it here. So it's very similar to the 1 prop Z interval of chapter 7, and all this information is still the same here. X1, N1, X2, N2. I just have to change the C level since I already did the test for this type of problem. There could be a problem where they only ask for the confidence interval, then you'd have to fill all the numbers in, but okay, so they don't give me, oh, they did here. Okay, I was going to say there's a way to figure out the C level if they don't tell it to you, but they just told it to me right here. It's 99%. So 0.99, and calculate. See how the interval is negative 0.06, comma, positive 0.04. So if this surrounds 0 like this one does, that's another way to say that there's not enough evidence to say the genders are different. In order for the genders to be different, if both of these answers were negative, that would mean that the second number is bigger. If both of these answers were positive, then that would mean the first number is bigger, and that would be evidence that either men or women are getting an advantage on calls. But if you want to agree that you're not rejecting the null and that the null could be true, that the genders are equal, then what you hope in the confidence interval is that, in proportions anyway, that one answer is negative and the other one's positive. If the smaller answer is negative and the bigger answer is positive, that means 0 is a possibility. So if I take the percentage of men that get the call overturned minus the percentage of women, if that subtraction equals 0, that the only way you get 0 in subtraction is if the 2 values are the same. Only 20 minus 20 is 0. If you're doing 20 minus 10 or 20 minus 30, if one number is significantly bigger than the other, then you don't get 0 in a subtraction. Oh wait, they want 3 decimals. Okay, so negative 0.62, 0.62, and 0.4, I think it was a 4, but let me double check. Yeah, 0.44. So at least that's easy in the calculator too. You can just run a 2 prop Z interval, not test, but interval. What conclusion is based on the confidence? So because the confidence limits include 0, 0 is included in that interval. 0 is between, remember the double less than means between. 0 is between a negative number and a positive number. When the confidence interval limits include 0, that's telling you that the null could be true. We assume the null will be true, but that we don't have evidence that the null is false when that occurs. So there does not appear to be a significant difference because it appears that they're equal and the genders are equal. So there does not appear to be a significant difference. That's what the ultimate goal in these problems is, to show there's a significant difference between them. And we don't have evidence that there is a significant difference. And we're doing this by a number of ways. Normally, if there was really some kind of like lawsuit or or investigation about something like this, they wouldn't do it in multiple different ways, but the book's just teaching you all the ways you could do this. They're blank evidence. There is evidence or there is not evidence maybe to warrant rejection of the claim. So there is not. There is not sufficient evidence to warrant rejection of the claim. The claim said that men and women have equal success. We can't disagree with that. If you want to reject the null and agree with the alternate, you have to have significant evidence that something's wrong with the null, not just a little bit of evidence. Just like in court, you're either not guilty as the null or you're guilty is the alternative, and it takes significant evidence to prove somebody guilty. We don't just put somebody in jail because it seemed a little weird. Based on the results, does it appear men and women have equal success in challenging calls? Yes, that's definitely true. The confidence interval suggests there's no significant difference. Men and women are getting treated equally, in other words. Okay, so now we get to practice this 2 more times. Problems 2 and 3 are basically the same kind of problem, just with different scenarios going on. So a study was conducted to determine if the proportion, see, it is about proportion, not about mean or standard deviation. You always want to focus in on that. Although if you look at the step 1 answers, they can tell you too. See how they got all P1s and P2s here? If it was about means, they would switch to mu1, and if it was about standard deviation, they would have sigmas. To determine the proportion of people who dream in black and white instead of color. So we had 324 people over the age of 55, and 73 of them say they dream in black and white. And among 229 people under the age of 25, 14 dream in black and white. So this is a yes-no question. Do you dream in black and white? And the 2 groups are people who are over 55 versus people who are under 25. So we're getting up towards middle-aged people versus people that are still young in their early 20s or late teens maybe. Use a 5% level of significance to test the claim. Test the claim that the proportion of people over 55 is greater than. See how they worded it this time? And they didn't say they're the same. It said they're greater than. And whatever's mentioned first should always be the ones. So if they say that people over the age of 55 are the first set of data I'm getting right up here, and then people who are under 25 come later, then that automatically means P1 is the over 55s and P2 is the under 25s. And the one issue with it is sometimes they'll word the question backwards. This one was worded, can we conclude or can we claim that people over 55 are greater than people under 25, which is exactly the order the data was given to me in. So that's why the alternative needs to be greater than. I'm looking for an alternative with a greater than right there. It's the only one of the 6 where there's a greater than in the alternative. And then the null is definitely equal to, because in the end that's always going to happen anyway. Technically it's less than or equal to, but don't pick that because it doesn't even have, they would never put one that has less than or equal to in the null and then correctly has greater than in the alternative. Otherwise you could argue that could be the answer too. So definitely the only answer here is E. They could, sometimes, I don't know if you'll see it in this, but I've seen in other textbooks where they intentionally word it backwards to see if you're paying attention. And instead of saying people over 55 are greater than people under 25, sometimes they'll say people under 25 are less than people over 55. And it really doesn't change the answer to part 1. It just, you got to pay attention to that. Just because you hear the word greater than or less than doesn't mean you're going to pick that one. Because if they word it backwards, then you have to do the other one. Saying that 25-year-olds are less than 55-year-olds is the same thing as saying that 55-year-olds are greater than 25-year-olds. So it's just due to the nature of inequalities that you can word it backwards and it can still be equivalent. Okay, so we're doing the test first. So that's stat tests number 6. All the problems in section 9.1 are number 6 here. 2 prop z test, and then also we'll probably do the 2 prop z interval as well, way at the bottom there, letter B. But they'll always do the test first if they're making you do both the test and the interval. So 2 prop z test, choose that one, and just watch out that the n has to be bigger than the x. So 329 people is actually n, and 73 is X. The 55 is just a qualifier. We don't use 55 anywhere. They could have said among 324 people who have red hair, 73 dream in black and white. So it didn't have to be about a number. So 324 is N1, but 73 is X1. 73 and 324. 73, 324. See, watch out for typos, otherwise you'll get the answers wrong, unfortunately. And then for the under 25 people, there was 290 of them and 14 dream in black and white. So 14 is X2 and 290 is N2. And this time we want the greater than option, which is the one at the far right. The three items at the bottom here that you have to choose one of these three. It should always match whatever you have right there in the alternative. P1 is greater than P2. If you successfully get that right, then you should definitely choose that one in the calculator. See how they have the P1 over on the left is greater than P2. Calculate. So now the z-test statistic is 6.28, maybe if they want 2 decimals, 6.28. Yep, 6.28. Now you're going to see some p-values like the one that just happened. I noticed it before I showed it to you. But 6.28, I don't know if you remember this, but back in chapter 3, we did something called the empirical rule. And the empirical rule was all about z-scores being in a certain range. In the empirical rule, 68% of the time, you are within 1 standard deviation of the mean, which is a z-score of -1 and +1. 68% of the time, you're in that range. And then 95% of the time, you're within 2 and -2. And 99.7% of the time, let me put it up here because I'm out of room. 99.7% of the time, you get a z-score between -3 and +3. It's very rare to, it actually goes all the way down to -infinity up to +infinity. But it's very rare to get any z-score bigger than 3 or less than -3, and I just got 6. 6 is incredibly far from normal. 6.28, you hardly ever see a z-score like that. And this is why, and I'll mention it now because people overlook this, but somebody's going to tell me on their test that the p-value is 1.7. But that's p-value stands for probability. It literally cannot be 1.7. Probability can't be bigger than 1. And this is not bigger than 1 if you look all the way at the end. Some students just don't look all the way at the end, how there's an e -10 here. The reason we're getting such a weird p-value is because you never see 6.28 for a z-score, really. It's possible, but it's so unlikely. So 1.7 e -10 literally means 1.7 times 10 to the -10th. That's the scientific way of writing it. And it means you have to take the decimal and move it 10 to the left. It takes 1 to get past that 1, and then there'll literally be 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9 before you get to the 1.7. And they usually like us to round p-values to 3 or 4 decimals. So whether I do 3 or 4, it's going to be 0, 0, 0. This is virtually a 0 probability. It's highly, highly unlikely this would happen. So the null says that the older people and the younger people dream in black and white equally. That's the null is always equal to. And if you get a very weird p-value, that's evidence that that's not true. We assume the null to be true, that both groups are the same. Unless we have strong evidence that something shows that's not true, we have very strong evidence here. The probability of finding 2 groups of people like this in the different ages to have the same black and white dreaming ability it's less probability than winning the lottery, actually. Because this is tenths, hundreds, thousands, 10,000s, 100,000, million. So if you have a 1 in a million chance of winning the lottery, that's right there, but we're still not even there yet. So there's 10 million, 100 million, billion. This is like a 1 in 10 billion chance. You have a better chance of winning the lottery than to see this happen. So this is exactly what these tests are all about, is we assume the two groups to be equal, and then we get some very low, very extremely low, weird probability. This shows that the assumption that the groups are equal could not possibly be true. Because if this is a court setting and the court sets you're assumed innocent until proven guilty, and now they have all this evidence that shows you're guilty, and if you try to tell the judge, hey judge, I know there's only a 1 in 10 billion chance that all this evidence would show that I'm innocent, believe me, I'm innocent because I never do anything bad. So maybe that's true, but the judge just isn't going to believe it, because why are you, the one person sitting in front of him, the 1 in 10 billion chance that maybe you're telling the truth when there's so many other possibilities that you're not telling the truth? So this is exactly what it takes. When the p-value is low, the null must go. The null is that they're equal, or in court settings, innocent or not guilty. But no matter what alpha they give me, this is going to be way less than any alpha they would ever give me. The alpha here is 0.05. So even if I add a 0 to that, 0 is less than 50. Definitely reject the null. The null says the groups are equal. I'm rejecting the null. And I'm saying that one group is greater than the other, that somehow older people dream in black and white more somehow. So not only when we get older does our vision start getting bad, apparently we lose color in our dreams too. I don't know if this came from a real study or if the author just made this up, but this is what sociologists do too, is they'll study cases like this and see if there's any evidence of it. Round to 3 decimals, 0, 0, 0 is what I'm rounding to, so it's virtually 0. It's not exactly 0 on the dot, but it's so extremely close to 0. So the p-value is less than the significance level of 0.05. So definitely reject the null. There is sufficient, or there is enough evidence. This book likes to say sufficient. Another book I use says there is enough evidence. So you might hear me saying that because I'm used to that. We can support the claim that people over 55 dream in black and white more than younger people. So in other words, younger people dream in color more often. And now, since we got the null rejected, then that means this confidence interval better be all negative or all positive. If the first one's greater, then it should be all positive actually, but it's only if it straddles 0 with one negative answer and one positive answer, then that's when you're not rejecting the null. So now I'm going to do stat test and go down to letter B, the 2 prop z interval. And all 4 of the numbers are still there because I typed them already in earlier in this problem. The C level might be different now. Now they want a 90% confidence interval, so change that to 0.90. See how the confidence interval is all positive this time. So 0.134 maybe, 13, yeah, they want 3 decimals, 0.134 and 0.220. When the confidence interval is all positive, that means the first values have to be significantly bigger than the second one, because when you do something minus something and get a positive answer, the first number is bigger. So that means the number of people who dream in black and white among the first group is significantly more than the ones in the second group, which is exactly what the hypothesis test told me as well. So the thing about doing both a hypothesis test and a confidence interval in the same problem is that it just confirms it. You would never get opposite answers by doing that. So because the confidence interval limits are all positive or greater than 0, they do not include 0. You only include 0 if one answer is negative and one answer is positive. Then it appears the two proportions are not the same, or however they're going to word this, they're not equal. Because the confidence interval limits include only positive answers, then people who are over 55 dream in black and white more often or greater than the people that are under 25. So, can the results be used to verify the explanation? An explanation for the results is that people of age 55 grew up exposed to media that was displayed in black and white. Well, that's somebody, maybe somebody's coming up with this as some possible explanation for it, but I don't know that just because we're seeing a big difference that we can just point to one possible cause. Maybe it's just as you get older, the same way your vision gets bad, maybe your ability to dream in color gets bad, and maybe you didn't watch black and white television when you were a kid. So see, this is one thing you want to avoid, is you don't want to jump to conclusions where you're picking out one possible only explanation. We would have to study this more to really see what's going on, probably. So can the results be used to verify this? No, probably not. People watched black and white televisions back in the day, but I don't think that caused them to dream in black and white. Maybe it does, but it would take more than this to prove that. So definitely it's one of these two no answers. The results speak to possible difference between proportions. They cannot be used to verify the cause. See, that's the problem. You can't verify the cause. The results speak to possible differences, but the results are not statistically significant enough. The results are pretty statistically significant. Anytime you reject the null, that means you have a statistically significant result. But no matter how significant it is, you can never talk about cause and effect, is what the point of this problem is, or this part. So it's about the cause and effect. We don't know the cause and effect. That would take much more study to know that. Okay, one last example of this. In a random sample of males, it was found 28 write with their left hands, 218 do not. Okay, I know why there's a third version of this problem. In a random sample of females, 69 write with their left hands and 469 do not. Use a 1% level of significance to test the claim that left-handedness among males is less than females. So I'm noticing less than right there, so probably you're going to pick the one with less than at the bottom, which is A. The only reason it would not be that is if they worded it backwards from the way it was given to you. But luckily, males were given first, and they're saying males are less than females. Just watch out if they give you males first, and then they say something about females, like females are left-handed more often. Even if you see the word like greater than or more than, you might not pick that one if the two groups are worded backwards in the question versus the data that was given to you. I don't know that I've seen that in other textbooks. Maybe this textbook doesn't do that, but it always tricks students when they do that and they just word the final question part where the claim is. Sometimes it gets worded backwards from the way the data was presented. Now, there's one other issue in this problem. And some people are just going to go right to their calculator and type 28 for x1 and 218 for n1 and 69 for x2 and 461 for n2. The problem is the 218 and the 461, these are not the sample sizes. These are basically, they asked people, are you left-handed? And some said yes, and the rest said not. That's a no. So they're not actually telling me the sample sizes here. They usually do, but this, I guess they were doing this to see if you're paying attention. If you take 28 plus 218, if you add the yeses and the nos, that's the sample size. They normally don't tell you the nos, but here they did. 28 plus 218 is 246. So x1 is 28. That's the number of people that said yes. But n1 is not 218, it's 246. And same thing for the women. There's 69 who said yes. There's 461 who said no. So the sample size for women is actually 530, not 461. Watch out for that. You probably wouldn't see this on a test, but the point, this homework problem is don't just fall for that whatever numbers they give you is always the numbers you need. So we need 28 and 246. And then we need 69 and 530. Let me take a picture of this or I won't remember all four of those. Okay. So go to stat tests number 6, the 2-prop z-test for the third time. So x1 is 28. N1 is 246, not 218. X2 is 69, and N2 is 530. So the only difference here is you have to come up with the ends yourself. They're not telling them to you. And now we got less than. So one good thing about problems 1, 2, and 3, problem 1 had a not equal to in the alternative. Problem 2 had it greater than, and problem 3 has it less than. So we got to see all 3 cases at least. Calculate. So the z-score is negative 0.64. If you would have plugged in the wrong ends, if you would have just blindly put the problem numbers in the problem, you would have missed that by quite a bit probably. Negative 0.64, I think they just want 2 decimals. Yeah, negative 0.64. So you remember how z-scores are between 3 and negative 3, and they're more likely to be between negative 1 and 1. 68% of the time they're between negative 1 and 1. So this is not an unusual z-score at all, so the probability of it is not going to be very low. It'll probably have a pretty high probability. The p-value is going to be pretty high, 0.261. So you only reject the null when the p-value is extremely low. It has to be less than whatever alpha they give you. And alpha is always between 1 and 10%. Here it's actually 1%. But I'm not less than that. I'm way greater than that, actually. So the p-value, do this again. The p-value was 261. Alpha is 0.01. They always give you alpha. Put another 0 there, but 261 is greater than 010. So fail to reject. Do not reject. Fail to reject the null. The null says left-handedness is equal. The alternative is trying to claim that it's less for men than women. But we don't have evidence that that's true. Fail to reject the null. Do not reject the null. That means there's not sufficient evidence to say that males have less left-handed people than females. The p-value is greater than the significance level, alpha 0.01. So fail to reject the null. There's not sufficient evidence to support that men are less than females in left-handedness. And that kind of makes sense because everybody goes to school and everybody favors one hand over the other when they're young. So the schools all try to force people to be right-handed, but some just stick to the left-handedness, but you wouldn't think that it would be different by gender. So now do the confidence interval. Now they want a 98% confidence interval. So stat tests, letter B, 2 prop Z interval. These numbers should all be good except for the 0.98. I should be straddling 0 again because we did not reject the null, and we are. See how the first answer is negative, the second one's positive. So this does include 0, and that means if it includes 0, that means the genders could be equal. And you can't say that one gender is significantly greater or less than the other one. So negative 0.75 all the way to positive 0.42. Because the confidence interval limits do include 0, there does not appear to be a significant difference. If it includes 0, that means you could say they are the same. So we don't have evidence that there's a significant difference. And that means there is not sufficient evidence to claim that males are less than females in being left-handed. Okay, so we did 3 examples. Wait, there's one more thing here. Based on the results, is the rate of left-handedness among males less? No, definitely not. It is not reasonable to conclude that the rate of left-handedness among males is less than. You needed significant evidence, a very low p-value to say that, and I don't have it. So it's not reasonable to try to claim that females are left-handed more often and males are less often. Okay, so that was section 9.1. Well, I had 3 examples in there. 9.1 is proportions when you have 2 proportions going on at once. Section 9.2 is when you have 2 means going on at once. This is when there's 2 means, not proportions, but averages. Well, the good news is the step 1 is done exactly the same way. All that's different is you put mu1 and mu2 rather than p1 and p2. And then the alternative can be greater than, less than, or not. It'll be one of these three only, not all three of them. But the good news is it's only one of those three ever. You always put equal in the null no matter what. And then the alternative is always just greater than, just less than, or not equal to. And then how you type it into the calculator is a little different because now there's a little bit more information. Now there's sample sizes still, just like proportions. But proportions only have x, the number of yeses. Means have a sample mean x bar and a sample standard deviation s. And in theory, they can also give you population standard deviation sigma. But this textbook never does because the author thinks it's an unrealistic situation. So an experiment was conducted to determine whether giving candy to dining parties resulted in greater tips. You know, they bring you the bill, and sometimes they put a little piece of candy on the little tray that it comes in. So does that, they're thinking of me nicely and giving me a little sweet, so maybe I'll give them a little higher tip. Is there anything to that or not? Or is it just all circumstantial evidence? So the mean tip percentages and standard deviations are given in the accompanying table with the sample sizes. So somebody did a sample at some restaurants, took a random sample of 25 dinner parties where no candy was given to them, and then where they got 2 candies. And notice that the average of the bill, or I don't know if this is the tip or the total bill, but probably the tip went a little bit higher when they got the candy, but is that a significant difference? Just because it's a little higher doesn't mean it's significantly higher. Okay, so assume the 2 samples are independent. Okay, and that's section 9.2. I should add that. Section 9.2 needs, this is an important topic, you need independent means. These have to be 2 independent means. Because in 9.3 we're going to do what happens if they're not independent. What if they're dependent? So these need to be people that just don't know each other. If you went to like some wedding and you had a whole bunch of tables where all these people knew each other, you wouldn't want to do that for this kind of problem because people tend to either be like, and if you have a very large family, they grew up with the same people raising them, so then maybe they're like tight with money and don't give tips out very easily, or maybe they're very loose with it and give out a lot of tips. So the problem there is you're more likely to be similar to relatives than total strangers. Okay, do not assume the population standard deviations are equal. Okay. I'm looking for the claim. The experiment was conducted to determine whether giving candy to dinner parties resulted in greater tips. See, greater tips right there. So that means now this is a little tricky because the no candy is listed first. See how when there's no candy, the average is 19, but when there is candy, it went greater to 21. The average got greater from the first one to the second one. But it's kind of backwards worded that way. So in order for the tips to be greater, that actually means that the first mean needs to be less than the second mean. The 19 is less than the 21. In other words, not just less, but significantly less. But that could trick you. You see the word greater tips here. Somebody's going to pick the greater than option on D and get this wrong. And it's all because we're looking for greater tips when there's 2 candies given, and the 2 candies are the second thing listed. That was what I was warning about. Sometimes they word this backwards. Okay, but one piece of good news for you guys versus other stat classes I teach at other schools is that this author believes that, let me show you the stat tests. In theory, you can do Z or T test in chapter 8, depending if you know sigma or not. Whoops. And then the same thing happens in chapter 9. It can be 2 sample Z or 2 sample T. You only pick Z if somehow the paragraph tells you what population standard deviations are. They have to give you sigma. This author never does, because he thinks, how would you know the population standard deviation? If you somehow knew that, why wouldn't you know the population mean? And then there would be no point in arguing about whether the tips are significantly greater or not. So this author only does T's, he never does Z's. So you'll never pick number 3, luckily. So the entire section 9.2 is all number 4, 2 sample T test. And this assumes that the groups are independent of each other. And you can do data like this. We'll probably do one of those in a second, but it can also, it's usually stats when they summarize it for you in a paragraph. So the first mean, X bar 1 was 19.08. And SX1 is the same thing as S1, which is the first S right here, 1.57. And both sample sizes, I think, were 25, but they can be different too. But 25 for the first sample size, it says right here 25. Then you put the second average in, 21.24. Then you put the second standard deviation in, 2.37. Whoops, I typed that wrong, didn't get the decimal, 0.37. And both sample sizes are 25. So it sounded like I should put greater than, but I ended up keeping this on less than. But always look what you have here, see, less than. So in general, means are a little bit harder than proportions. In some textbooks, they're a lot harder. You guys will have it a little easier because you don't have to worry about Z or T. Every problem for you is going to be T. But it's a little harder because you have to decide between data and stats, and you have to decide, not decide, but there's just a few more numbers to type in, and if you get it in paragraph format, you might not know which number goes with which variable. Here they were nice enough to make a table and list everything for you the first time. Now, one last thing too is after you choose either not equal to, less than, or greater than, this two-sample t-test is the only one where it has this extra question about pooled. It'll say pooled, no or yes. So note, have you ever heard anybody say to you, here's a no-yes question for you? Nobody ever says it that way. They always say, here's a yes-no question for you to answer. Or I've numerous times when I was doing proportion problems said, these are always yes-no questions. Everybody always says, this is a yes-no question. Nobody ever says, this is a no-yes question. But notice no is listed first here. The reason for that is the default is no. If somehow the paragraph doesn't mention the following, then the default is no. But at the very end, there's this last little phrase that says, do not assume the population standard deviations are equal. Only two sample t-tests mention that little phrase. This is so you can say yes or no to pooled. And you only say yes if they somehow tell you, assume the population standard deviations are equal. That's the only time to say yes. But usually they just say, do not assume that they are. Then you're definitely going to say no. Or if this is just not mentioned at all, then the default is no. And if you click yes or no wrongly, then you'll get the p-value wrong, unfortunately. But this one should be no. Now you hit calculate. So look at that. I always look at the end of the p-value. I'm looking for any E negative because they come up sometimes. Whenever there's an E negative p-value, that means you're very close to zero, and you're probably going to reject the null. This is saying the two groups are significantly different from each other. So it seems like 2.32, but it can never be 2.32 because probability can't be bigger than 1. It's 2.3 E negative 4. 2.3 E negative 4. So move this decimal over 4 times. 1, and then it'll take 3 more, so you'll get 3 zeros. It's actually 0.00023, and so on. But if we only want the first 3 places, it's not even going to bump up. Now this 2 could have been like a 7. Then I would put 001. So you got to watch out for that. But this will still be 000. Almost every time you get an E negative p-value, it's almost always going to be 000 for the p-value for us. Although they only want 2 decimals here. So, oh wait, I need the test statistic first. So I didn't answer that part, but the test statistic is right here. T equals negative 3.799, so make that 80. Negative 3.80. And remember, see, they usually don't go past 3. We're already past 3s already, negative 3.80. And that's why this p-value is so low, 000. So we are rejecting the null because we have a very low p-value. If the p-value is low, the null must go. Reject the null. If you do reject the null, then there is sufficient evidence. If you do not or fail to reject the null, then there's not enough evidence. It's always one of those two. You would never say reject the null and there's not enough evidence, or do not reject the null and there is enough evidence. B and C are impossible answers that you would never put. So that's what's nice about the p-value method, is there's only two endings. If the p-value is low, then you reject the null and there is enough evidence. If the p-value is not low, then you do not reject the null and there's not enough evidence. And then you can do a confidence interval too. So this was the 2-sample t-test. I can do the 2-sample t-interval, which is number 10, 2-sample t-interval. And all the data should be here since I already did this problem for a test already. So the only thing I might have to change is the C level. The C level is... Okay, they didn't tell it to me. There is a way to figure it out when they don't tell it to you. Okay, so if the alpha level of significance 0.05, if that, they have to give you that for sure. And then it depends if they give you a 1 or 2-tailed test based on what you have in the alternative. The alternative I have is less than. If you get just less than or just greater than in the alternative, that's called a 1-tailed test, because then you only care about that one side of the curve. If you put not equal to in the alternative, then it's called 2-tailed, and then we care about both tails. So only if you're doing a confidence interval and they don't tell you the C level, you have to do this. My problem gave me an alpha of 0.05, and I had a less than alternative. Less than's on the left side here. So then you put the entire alpha in that tail. If it's 1-tailed, you put the whole alpha in that tail. 2-tailed, you actually cut it in half. Now, even though I only care about the less than side, by the symmetry of the graph, there is another 0.5 in this tail too that I just don't care about for what I'm trying to do. But the C level for confidence intervals is always the middle portion of the curve. So I need to know both tails just so I can figure out the middle. The middle will always be 1 minus both of the tails. And this is why it's a 90% confidence interval. The middle is always the confidence level of chapter 7. They usually tell it to you. Every problem so far has told it to me, but for some reason this one didn't. And at first, when I was doing number 1, I wasn't sure if it was there, and I thought I was going to have to show you this, but some problems luckily are telling me the C level here. They didn't. So that's why I know this is a 90%, since they didn't tell me that, but 0.90. And pooled will still be no, because they said that already. I'm using the same data from the first half of the problem. If somehow you had like a separate problem where all you were doing was the confidence interval, then you'd have to start all over from the beginning. But notice the answer is negative 3.116. Oh wait, 2 decimals, okay. Negative 3.12. Negative 3.12. And negative 1.20, and it's all negative. So that means it can't equal 0. If this subtraction is always negative, that means that the first number has to be smaller than the second one, significantly smaller. The $19 tip is significantly smaller than the $21 tip because this is always negative. And that means giving the candy was worth it. The waiter or waitresses are getting more money by putting that little candy there. Sometimes they like draw a smiley face or leave you a little message on the receipt. I'm noticing Starbucks is now writing messages on the cups before they give them to you. So they think that gets them more tips, and maybe it does. There may be something behind this. We can do a hypothesis test to check, and this could just be made up for this textbook, but we could maybe do this in real life and see if it really makes a difference or not. Does the confidence interval support the conclusion? Yes, it does. Because the confidence interval does not contain 0, it contains all negatives. It's only negative. And that means no matter what happens in your sample, the answer is going to be always negative, which means the first mean has to be smaller than the second mean for that to happen, significantly smaller. Or another way of thinking about it is the second one has to be significantly bigger than the first one. So that means you're getting a significantly bigger tip. Okay, this is the same thing, except instead of putting it in a table, they kind of summarized it here. So researchers conducted a study to determine whether magnets are effective in treating back pain. Can I put a magnet on you and have your back pain go away? The pain was measured using a visual analog scale, and the results are shown below. Higher scores correspond to greater pain levels. Assume the two samples are independent. And here it is again. Do not assume the standard deviations are equal. That means you're going to say no to pooled again. Okay, so there was pain level after the magnet treatment, and then there was pain level after somebody got a sham treatment like a placebo. So the first mean was 0.57 with the magnets, and it was 0.52 without the magnets. So those two numbers don't seem all that significantly different from each other. Now this one's a little vague in terms of the alternative hypothesis, because the claim isn't saying anything. Oh wait, no, that's about the pain levels. Researchers conducted a study to determine whether magnets are effective. Now what does it mean to be effective? Does that mean your pain level is significantly smaller? Or maybe it says it down here. Oh, here it is. Yeah, I was looking for the claim. Test the claim that those treated with magnets have a greater mean. Oh, this is about reducing the pain. Okay. So I was thinking, why would you want the magnets to make the pain higher? Then who would go through that? But it's not about a higher pain. It's about a higher reduction in pain. And the magnets did get a slightly higher average, 0.57 versus 0.52, but maybe that's not a significant amount. But the magnets are first, and it says greater than, and it's asking if the magnets are greater than, so then that's where it's worded normally. So then you're looking for the one where there is a greater than right here. Okay, so let's run this in the calculator. Let me see if I can put it where we can see it all at the same time. Whoops, there. Whoops, oh, I had it and lost it. Well, try that again. Nope, it's not doing it. Wanted you to be able to see this while I'm typing it, but right there, I can't grab onto it. There it goes. Okay, whoops. A little better. There. This is how I was trying to grab it. Wouldn't let me grab it. Okay, so now I got to move it a little. Hope it doesn't blow up. Okay, so stat tests, two sample t-test, because we have independent samples here. And this is still stats. Anytime they summarize these numbers for you, it's stats. If they listed all 25 of these answers and all 25 of those, that's the only data problem. So I don't think you're even going to see a data problem for these because it would just take too long. Okay, so X bar 1 is whatever the first mean is, 0.57. The first S is 1.03. The first sample size is 25, and it's not that they always have to be 25, but they're using 25s again. So the second mean is 0.52. The second standard deviation is 1.54. And then there's another 25. And this time I had greater than, so I got to go to the third slot way over there to the far right and click that. And keep no to pool. Now, I think they're going to always give you no, but calculate and you'll get the t-test statistic. It's 0.1313, which is very close to 0. So this is not an unusual one at all. So I'm going to get a pretty high p-value because of that. The p-value is 447. 447. If there was a 44% chance of rain and it rained, you wouldn't be shocked. How did it rain? It's not that it's guaranteed it's going to rain, but what we're looking for is a very low p-value. If they say there's a 1% chance of rain today and then it rains, you'd be pretty surprised. How did that happen when the chances were so low? That's what we're looking for here. Only when the p-value is unusually low do we have something unusual going on. When the p-value is anything normal, like 20%, 30%, 40%, even higher than that, then there's nothing unusual going on. We assume the null to be true. It doesn't make it true, but we assume that the magnets do not help back pain unless we have strong evidence that shows that they do. The only strong evidence we can get is a very, very low p-value. This is not a low p-value at all. So do not reject the null. Fail to reject the null because this p-value is way greater than any alpha they would give us. And they gave us 0.01. We're way bigger than that. So there's not sufficient evidence to claim that the magnets help with reducing pain. So now do the confidence interval, stat test number 10. And the only thing possibly to change is the C level. And again, they're not telling me what it is. So then, see, I got to look here. It's a greater than, so then you only care about the greater than side of the graph. Exactly like this. Okay, I can blow this up, I guess. Okay, let me change it back here. So we got the greater than side. Alpha's 0.01 this time, so put the 0.01 on the right side. And then by symmetry, there's another 0.01 on the other side, even though I don't care about that for what I'm trying to do here. But if I do 1 minus 0.01 and minus 0.01, that'll tell you the middle percentage, which is the C level that I need in the calculator. So that's why this is a 98% confidence interval. Whoops. So go back to the calculator and put 0.98 in. Say no to pooled and calculate. Okay, so the confidence interval is not all negative this time. It's negative 0.846, negative point, oh, they want two decimals, negative 0.85, but the other one's positive 0.95, if you round to two decimals, 0.95. So it straddles zeros. Zero is a possibility. If you take two numbers and subtract them and the answer is 0, that means the two numbers had to be the same. So whenever the confidence interval has 0 inside of it, that means 0 is a possibility, and that means the two numbers could be equal to each other. So the magnet pain reduction level could be the same as the non-magnet, so then the magnets don't make a difference. If it was all negative or all positive, then one is better than the other one. Does it appear magnets are effective? No. They're not effective because 0 is in the confidence interval. Is it valid to argue that magnets might appear to be effective if sample sizes are larger? No. Increasing the sample size will increase the p-value. It's definitely not B, because B says the magnets already appear to be effective. They don't seem to be effective. So maybe that's one thing that could be true, actually, is that if these are relatively small sample sizes, 25, so increasing the sample size could actually help here. Is it valid to argue that magnets might appear to be effective if the sample sizes are larger? Increasing the sample size will increase effectiveness. Well, here's what we could do. What if I change, let's go back and see what happens to the p-value if we change the sample sizes to larger amounts. Whoops, I picked the wrong one. Stat test number 4. The sample sizes are 25 and the p-value was 0.44. So what if I double them to like 50? This is what's nice about technology. You can try something like this and see what happens. If I keep everything the same, but I double if I double the sample size, what happens to the p-value? It got a little bit smaller, see, 0.42 instead of 0.44. So one of the choices says yes, because increasing the sample size will decrease the p-value. Now, the only issue, though, is it decreased it a little bit, but it's still really far away from being effective. So, but there's a keyword here, might appear to be effective. See, so D can't be the answer because it says because increasing the sample size will increase the p-value. That's not true. And definitely B is not true. So it is one of these two yeses. Increasing the sample size will increase the effectiveness. It's hard to say if that's true, but so I'm going to go with A, and if it's not that, then it's the other one. Okay. So yeah, that's a good way to check this if you don't know, is you just try an example and see what happens. That helped me to know that A was possible and D was impossible, and I wasn't sure about C, but okay, one more of these. Here's one last problem from 9.2. Again, the summary data is all here on the side. Test the claim that males and females have the same body mass index. So that means the null is equal to only, and that the alternative has to be the opposite, not equal to. So males and females have the same body mass index, or they don't have the same. That's the null. So let's run this in the calculator. Both sample sizes are 42. They have different means and different standard deviations. Slide this over so I can see it. Okay, so stat tests number 4. X bar 1 is the first average, this 28.1888. The first S is 8 point, I would use the whole thing, 8.018682. Both sample sizes are 42. Now the sample sizes don't have to be the same, but every example we've seen so far has had them the same, but it would be okay if one was 42 and the other one was 43 or something even different. So X bar 2 is 25.5521. S2 is 5.103749. And then another 42 sample size. And then definitely not equal to. And I'm assuming it's still going to be no, but let me double check. Do not assume the population standards are equal. So yes, say no to pooled and calculate. So the t-test statistic is 1.80 if you round that up, that 79 up to 80, 1.80. So I am still between 3 and -3, but I went past the 0 point numbers and I'm almost out to 2, but that's probably still not that significant. The p-value won't be as high as that 0.44 of last time, but I don't think it'll be all that low either. Well, it could depend. 0.077, 077. The three most common alphas are 0.1, 0.5, and 0.10. So if I get 0.1 or 0.5, I'm going to get a different conclusion than if they give me 0.10. That can actually affect the answers sometimes. And they gave me 0.05 right there, 0.05 significance level. If they would have given me 0.10, I would have had the opposite answer, but 0.077 compared to 0.05. If you add another 0, then you're comparing 77 to 50. 77 is greater. The p-value is not low, it's not less, so the null does not have to go. Do not reject the null, and there's not enough evidence, is how I normally word it, but that's a good way to remember that. If the p-value is less, the null must go. If the p-value is low, the null must go, and then you do reject it, and then there is enough evidence. If it's not less, if it's not low, then it does not have to go, and you do not reject it, and there's not enough evidence. So fail to reject the null, which always goes with not sufficient evidence. You would never say fail to reject and there is sufficient evidence. That never happens. Okay, let's do the confidence interval. Stat test number 10. And it's good that you're seeing this one because the C level is done differently than the other two. So I got to get the C level is the only thing different here. And this is a two-tailed test with an alpha of 0.05. But it's two-tailed because the alternative was not equal to. Whenever it's two-tailed, then you actually care about both tails. But the 0.5 can't change, so you have to divide the 0.5 in half. You only do this when it's two-tailed. So that way there'll be 0.25 in each tail. That way combined, it still adds up to 5%. So if the alternative is only less than or only greater than, then you put the whole alpha in that tail, and then you basically copy the same amount on the other side. But if it's two-tailed with a not equal to, then you cut alpha in half and put that in both tails. If you need to find the sea level is the only time you do this. So the sea level will actually be 0.95 this time. 0.95. And I'm going to assume no to pooled. Come on, go down. Calculate. The t-score is... Oh no, we're doing the confidence interval now. So negative 0.2888. 3 decimals, so negative 0.289. And positive 5 point, 3 decimals, I thought I said 2, but 5.562. 5.562. See, zero's in that range again. And anytime you say do not reject the null, the zero should be in between the two. So the confidence interval, does the confidence interval support the conclusion? Yes, it does. Wait a minute. The conclusion was what? That they have the same body mass. So that we can support that conclusion. Yes, they have the same body mass because the interval contains 0. So that means they could be equal to each other as they claim. They claimed that men and women had the same, and we can agree with that conclusion. Okay, so there's only 4 problems left. There's 2 problems from 9.3, and then there's 2 from 9.4. I'm actually going to do the 9.4 first because it's another one that you can do in the calculator. It turns out 9.3, you can do it in the calculator, but there's not a built-in direct test for it. And since I'm at a good stopping point right now, let's do our magic word of the chapter. We got 3 chapters to go, 9, 10, 11, so these next 3 magic words will all be of the same theme. We had cities in the first unit, and then I did sports teams in the second one, and then the last one was about seasons of the year. So this time I'm going to go to planets of the solar system. The crown jewel of our solar system, according to scientists, is the planet Saturn because of its pretty ring system that you can see from Earth even with a moderate telescope. So the magic word of chapter 9 is Saturn. Email that to me. Okay, so 9.4 is about standard deviations. First we did proportions, then we did means, now we're doing standard deviations. So words were displayed on a computer screen with background colors of red and blue from the scores of a test. Use a 5% level of significance to test the claim that samples from populations are with the same standard deviation. So the claim is that they have the same standard deviation, which means they're equal, which is always in the null. But since the claim is that they're equal, then that means the opposite is they're not equal to, so then the choice would be A. Okay, this one you can do in your calculator. It's pretty easy to do. You go to Stat, Test, and if you up arrow, you'll get there faster because it's like the way towards the bottom. And you might have a few more things at the bottom of yours than mine because this is a very old version of the 83s, more than 10 years ago. But you might have a few more things at the bottom, but you should have one near the bottom called 2-sample F-test. The 2-sample F-test is used in section 9.4. Okay, so we need to put in the S, the N for both of them, and then clearly the alternative is not equal to because I said that already. Okay, so there's S's and there's X bars and there's N's. Turns out you don't even need the X bar even though they gave it to me. So let me show you here where you can see both at the same time. So SX1, that's the first S, 5.91. And clearly the first N is 34. You don't need X bar. The second S is 5.49. And the second N is 37. See how they don't have to be the same? They just, every problem we saw so far they were, but they don't have to be. And then you click not equal to if it's not there already, and that's it. There's no yes or no to pool to just calculate. And instead of getting a Z or a T, you get an F. F is the test statistic, 1.16. If they want 2 decimals, yeah. 1.16 is the F test statistic. And then right below that's the p-value. 664, if you bump this 3 up to a 4, 664, that's a pretty high p-value. 664 and 1's pretty small F score. So do not reject the null. Fail to reject the null. 664 is way less than any alpha they would give me. The alpha here is 0.05, so I'm way greater than that. The p-value is a lot greater than alpha, so do not reject the null. Fail to reject the null. There's not enough evidence. There's insufficient evidence. Does the background color appear to have an effect? No, because we're agreeing with the null saying that they're equal. So if we would have rejected the null and said that they're not equal, then we could say one color is better than the other, but we can't say that here. So no, the variation of word recall appears to be the same when they change the color. I get the same for both regardless of the color. So those go a little quicker than the other problems because they don't make us do a confidence interval, luckily. And okay, so now same kind of problem, just different scenario here. Researchers conducted an experiment to test the effects of alcohol. Errors were recorded in the test of visual and motor skills for a treatment group of 22 people who drank ethanol and another group of 22 who were given a placebo. The errors for the treatment group have a standard deviation of 2.1 and the errors for the standard deviation of 0.83. See how they're just summarizing it in a paragraph instead of like listing it for me. Assume the two populations are normal. Okay. Use a 5% level of significance to test the claim that both groups have the same amount of variation. Have the same. So this is exactly like the previous problem for the step 1. The null is that they're equal, and then the alternative is the opposite of that, not equal. So here you kind of have to read the paragraph to get this information. Stat test, up arrow to the 2 sample F test, and keep yourself on stats and not data. The first standard deviation is this 2.10 right here. 2.10. And both sample sizes are 22. There was a group of 22 and then another group of 22. So let me see if I can put it here where you can see better. So both sample sizes are 22. And the second standard deviation is this 0.83 right here. 22. And it's not equal to again, so calculate. So these ones are pretty easy to do in the calculator. The F test statistic will come up first. 6.40, that's a little larger than the last one. Now these I think can go past 3 a little more commonly than the Z's and the T's. But 6.40 is definitely larger than that 1.16 I got a second ago. So let's see if that makes the p-value really low. Yeah, see the p-value is very low, 7.7 E negative 5. 7.7 E negative 5. The p-value is 7.7 E negative 5. Which would be 0.00077. There'd be 4 zeros. Whatever the E number is, it's 1 less 0 than that because it takes you 1 place to move past the 7. But if I round to 3 decimals, this is all 0. If you rounded to 4 decimals, this would bump up to a 1, but I think they want 3 decimals, so 0, 0, 0. The test statistic is so high that the p-value gets really, really low. And that's lower than any alpha they would give me. 0 is definitely less than 0.05. So now we reject the null, and there is enough evidence. There is sufficient evidence to say that something's going on here, that the people that drank alcohol are different some way than the people who drank the placebo. Okay, but that's all they had me do there. I didn't have to finish that. So only thing left is 7 and 8. This is what happens if you have dependent samples. We're going back to means now. Remember that section 9.2 was independent two means. Now we're going to do dependent with two means. And the classic example is a before-after study they do often in medical situations. So you have somebody with high blood pressure, you have a group of people with high blood pressure, and then you measure their blood pressure at the start, and then you give them medicine or diet or exercise, and then you come back and measure them after the treatment. And we hope that their blood pressure goes down. But the problem is it's the same people both times. So if you have really high blood pressure, it's easier to get yours to come down than if you don't have really high. These are not independent when it's the same people twice. So let me do the classic example first, number 8, the before and after. So this is the only time in all of chapter 9 that we have raw data given to us. Instead of summarizing all the information in the paragraph in one way or another, they just told me of the people surveyed, this is the answers. And they don't have a test in the calculator for this directly. So the way you do this is first go to Stat, Edit, and if you have data in here, go up to the top and hit Clear Enter to clear it. So first you have to type all the numbers in the first two lists. I have to put 6.9 and 4.3, 11.3, 8.7. The befores go in L1. 12.6. Watch out for typos, otherwise everything will be wrong. See, I almost had one right there. I put 98 point instead of 9.8. 7.2 and 0.3. All the befores go in L1. All the afters go in L2. 6.5, 2.8, and they also, you don't want to sort these. Wherever the 2.8 is, it has to be next to the 4.3 because that's that one person. Somebody had a 4.3 and then they dropped a 2.8, but that person, their information needs to stay together. So the 7.6 has to be next to the 11.3. The 8.2 needs to be next to the 8.7 and so on. And then I got another 8.2. This 8.2 has to be with the 12.6, 6.1, 3.9, and 2.1. Okay, so you put your data in L1 and L2. The null is that the mean difference equals 0. We're going to take these two scores and subtract them. I want to take their before scores minus their after scores and see what happens to the subtraction. Say you have high blood pressure, and we measure you before your medicine or before your diet or before your exercise, and you have some kind of blood pressure score. And then what if the medicine doesn't do any good and your score stays the same? So then if you do the first score minus the second score and they're both the same, you're going to get 0 for an answer. So if the mean difference is 0, that means the medicine or the diet or the exercise does not help. But if the mean difference is either less than 0, greater than 0, not equal to 0, then we can say some kind of effect was good. So they always put mu d, although here they're doing, okay, they're doing a confidence interval and not the one I thought that we were doing here. Okay, so, but still we can do this. It's not built into the calculator, but here's how you do it. So you go to L3, go up to the top of L3, and you do L1 minus L2 by hitting second and the number 1 and second and the number 2. This will do all the subtractions for you. So it just took 6.9 minus 6.5 and got 0.4. 4.3 minus 2.8 is 1.5. Notice that every subtraction is some kind of positive number. Oh, there's one negative at the end, but they're mostly positive. So if the answers are all or mostly positive, that means the first number is bigger than the second one. And then that would be good if you had like a high blood pressure and you're trying to make it go down to a lower blood pressure, or a high weight trying to get somebody on a diet and get them down to a lower weight. So if you were doing a test, I thought we were doing a hypothesis test here, then this question would probably have the greater than one right here, because the first scores are bigger than the second ones, and that makes the subtractions positive, and positive subtractions are greater than 0. But we're actually doing a confidence interval instead of what I thought it was. So go to stat tests. Now it turns out, even though you have 2 samples, they're dependent samples, so this 2-sample t-test doesn't work if we ever get a problem that involves a test. But if you use L3 only, then you can trick your calculator and just do a regular t-test. So the same thing should be true for the interval. You might think that it's a 2-sample t-interval, but that only works if they're independent. So I'm just going to do a regular t-interval and trick the calculator into thinking that there's only one data. By going to data instead of stats, press enter. And for the list, tell it L3, because then it'll think that's its whole data. It won't even know L1 and L2 exist. And the frequency, we always leave that as a 1. The C level can be anything. So let's see if they told it to me. Yeah, they said 95% right here. And that's what it defaulted to. So I'm good to go here. Calculate. So the lower number is 0.155, round to 2 decimals, so 0.16. And the bigger number is 3.77. So that's all positive. That means if the answer is all positive, that means the first numbers are significantly bigger than the second numbers, because then when you subtract, you'll get a positive answer. A bigger number minus a smaller number is positive. And if the befores are like people's weight or their blood pressure, and I put them on a diet or medicine, and now their second numbers went down, that's good. That means the medicine or the diet's working. Does hypnotism appear to be effective in reducing pain? Yes, because the pain went from higher numbers down to lower numbers. The confidence interval did not include 0, and it's all positive or greater than 0. So that shows there's a significant difference here. So number 8 only was having you do a confidence interval. I thought they were going to have us do the test too, but they only did the confidence interval. This is the test right here. So you always put mu d equals 0 in the null no matter what. There's no other possibility for that. The alternative is definitely compared to 0 as well, but it could be greater than 0, less than 0, or not equal to 0. You definitely would never put an equal to there though. So this is, instead of before and afters, this is actresses versus actors in, like, say, the Academy Awards. So in a given year, are the actresses younger than an actor? Because there's kind of bias on gender like that. If a woman's young, then she's supposed to be pretty. And then when women get older, then they're not as picked to be in movies anymore. At least in the past, that was the case. But you could get old actors and they would still get very good jobs even when they got really, really old. Somehow when men aged in the movies in Hollywood, it wasn't a big deal. They could still get good jobs, but the women wouldn't get the good jobs and wouldn't get the awards unless they were really young. That could be a case of gender discrimination. Maybe a lawsuit could be formed because of that. The following data lists the ages of a random selection of actresses when they won an award, and then along with the actor in the same year. So is there any kind of bias from year to year is kind of what's going on here. Use the sample data with a 1% level of significance to test the claim. Test the claim that the ages of actresses and actors, that the differences have a mean that's less than 0. So see, they spelled it out right there for us. We want less than 0. If the mean difference is less than 0, that means the first numbers are smaller than the second numbers. And that means the actresses are younger and the actors are older, which, if it's a significant difference, that could be some gender bias right there. You could get a class action lawsuit going, possibly. So here's the deal here. So you do this basically the same way. Put your data in L1 and L2 and clear out. You don't have to clear out list 3, but clear out L2 and then go over and clear out L1. Type the new data in L1 and L2. So L1 is 29, 31, 28, 30. Go faster this way, 33, 23, 28, 38, 31, and 32. Whoops, I didn't type that one right. 32. Okay, that was the actresses. Now the actors, 62. See, that one was a lot older than the woman that won that year. 39, 34, 37, 30, 31, 54, 39, 39, and 40. So not only are they always at least a little older, sometimes they're significantly older, what appears to be significant anyway. So you always put your data in L1 and L2. Then you always go to L3, and even if there's data here already, you don't have to clear it out. If you go to the top of L3, see, not where the point 4 is, but go all the way up where the L3 name is. Type second and the 1 for L1 minus second and the L2, and press enter. It'll zap over the old ones. And then you can either do a t-test or a t-interval to get this answer right. So they don't have one built into the calculator to do a 2-sample dependent samples. So we trick our calculator by pretending we just have one sample, even though this is technically in chapter 9 where there's 2 samples. So either go to t-interval if they want an interval, or go to t-test if they want to do a hypothesis test, and click on data, not stats. Luckily the mu d, or they're putting mu 0, but it's really mu d, it's always 0, so just leave a 0 there. Always make sure your list says L3 if you're doing this section 9.3. Always leave the frequency as 1. And then we had what for the alternative? We had less than. The actress's age on average is less than the men, and significantly less. So that would be a gender bias if women have to be younger to win awards and men can win them even when they're older. So calculate. The t-score is negative 2.95, which is getting out there towards 3 now. Negative 2.95, usually you don't go past negative 3 or positive 3. We're getting out there close to negative 3. And that made the p-value pretty small too. The p-value was, it wasn't quite one of those E negative numbers, but it is still pretty small. It's 0.008. If there was one more 0 involved, they would have wrote it as a scientific notation answer, but 0.008. That's a very low p-value. The alpha here was 0.01. So here's one that might trick you if you don't do this carefully. The p-value here was 0.08 and alpha's 0.01. I see people on tests get tricked by this all the time. They try to tell me that 8's greater than 1, which normally it is, but you don't have a fair number of decimal places to compare. This has 3 decimals, this only has 2. So add that extra 0 to the end and it makes a difference here. Now 8 is less than 10. The p-value is less than alpha. The p-value is low, so the null must go. Reject the null. Reject the null because the p-value is less than or equal to the significance level. So reject the null. And there is sufficient evidence then to say that actresses are generally younger, and that could be some kind of gender discrimination possibly. That this could be used in a court. And now they want me to do the confidence interval too. So now go, instead of t-test, go to t-interval for that. Stat, tests, t-interval. Because remember, we never do z's in this book. It's always t's. And the only thing you might have to change here is the 0.95. Let's see if they change that. Okay, so it's another one where I have to figure it out myself. There's a 0.01 significance level, and I have a less than. Less than is a one-tailed test. One-tailed less than. So put the whole O1 in the left tail. Whenever it's one-tailed, you put the whole alpha in that tail. And then by symmetry, there's another similar amount on the other side. And that will allow you to figure out how much there is in the middle, which is the C level that I need in the calculator. 1 minus O1 is 0.98. So they didn't tell me do a 98% confidence interval, but I can figure it out by doing this little chart right here. So that's why I need 0.98 here, not 0.95. If you do the wrong decimal percentage, then it'll be wrong, unfortunately. Calculate. So this should be all negative. It should be all negative because that means the first numbers are smaller than the second. And see, it's all negative. It's negative 19.95 and negative 0.4462. Negative 19.9, oh, they want one decimal. So negative 20.0, because 19.95, the 5 is going to bump the 9 up. This 5 will bump the 9 up, but it'll turn the 199 into a 200, basically. And to one decimal here, it's negative 0.4. But the more important thing is that's all negative. If that's all negative, then that means no matter what turns out, the first numbers are always going to be smaller than the second numbers, which means that the actresses are younger. In order to win, they have to be younger, and that's not fair. They should be just as good when they get older, too. What feature of the confidence interval leads to the same conclusion? See, it is always the same conclusion. Since the confidence interval contains all negatives, only negatives, that's why you reject the null. Only when it contains 0 do you not reject the null, because that means it could be higher or lower, then you can't say anybody's being discriminated against. So there's all 10 problems. We only had 10. This was the shortest homework of every chapter so far based on number of problems, and yet it may have been the longest video we've had so far. This video was a little more than an hour and a half, but at least you've seen all 10 problems now.